Here, great. Alrighty, so our favorite lab time. So today we're going to start our first of two magnetic field labs. So basically in this lab we're going to be playing mostly with observations and things, trying to see how things change and how things work, and then trying to get an idea of the distance dependence for magnetic field. So first of all, what is a magnetic field? So a magnetic field is, much like an electric field, it is a vector field, which again means that at all locations in space, so here's my space, it has both a magnitude and a direction associated with it. So there's going to be some magnitude of the field. So magnetic fields we always write as a B. So this is equal to the magnitude of the magnetic field. Magnitude of the field. And then it has some sort of directional property to it as well. So my point, say, in this direction. Okay? Now, unlike electric fields, though, magnetic fields are actually generated by moving charges, not stationary charges, i.e. current. So magnetic fields are actually going to be generated by current as opposed to stationary charges. I remember an electric field, all we needed was some sort of stationary charge. So we know that this thing was proportional to stationary charges. But a magnetic field has to do with actually current, so moving charges. So current. So current is what actually generates them. There's other differences. We're going to talk more about these in class, but for example, one other difference is that electric field lines move in straight lines. So the field lines move in straight lines. And one thing that this lab wants you to see, which is kind of hard to see because we're only going to be watching videos, but it turns out that the field lines for magnetic fields move in circular closed lines. So these move in closed circles. So basically, so again, if I was thinking about a charged particle, we know the electric field line points radially out in all different directions. So this is our electric field. But it turns out for a magnetic field, so if this is, say, a wire which has current moving through it, what happens is that the magnetic field actually creates closed circular lines, where my closed circular lines are going to do something like this. So this is actually what our magnetic field does. It actually goes in circles, but again, we'll talk more about this as we go through. Now, also for electric fields, we know that to sample the direction of an electric field, we use test charges. Right? So as we talked about in class, what we do is we put a test charge into some sort of electric field configuration. So here's my electric field configuration. We throw in our test charge of positive charge Q, and we look at the force on this thing, and then we know that the electric field points in the same direction as the force. Right? So by watching how this thing actually moves in the direction of the force, then we can determine the electric field. For magnetic fields, it's very similar, except now we're not using test charges, but we're actually using compasses. So a compass is actually a bar magnet. So what a compass is here's my compass. What it does is we have a bar magnet, and that bar magnet has a north pole and a south pole, which means the magnetic field points away from the north pole and then points into the south pole. So this is the direction of our magnetic field, creating closed lines. So basically my magnetic field is either going to curl in this direction or curl around in this direction. So basically what we do is inside of here, we're going to put in our compass, and then the direction at which the compass needle points will be in the direction of the magnetic field. So here our magnetic field will point this way, which means that this is the direction of the force, because it's actually going to create a torque. That torque will align itself with the magnetic field, so the direction that the north needle points will be in the direction of the overall magnetic field. So how we sample the magnetic field is also very similar. We're going to use compasses as opposed to test charges. Okay. So these are some kind of similarities between magnetic fields and electric fields. Okay. Now, what's going to be different about this lab as opposed to the other labs that we've done is I have not been able to find a good simulation for magnetic fields, unlike all the other labs that we did. So in the other labs, you know, they weren't the most ideal thing, but they worked well enough because we were actually looking at simulations that actually simulated everything. For magnetic fields, the only thing I could really find was you're moving a compass around in an external magnetic field and you're watching the direction in which it moves. That's it. So we there's not really much to do. So basically, when you go onto Blackboard, what you'll find is a playlist of the videos. Those videos are videos that we're taking at the end of this previous semester when all this COVID-19 stuff happened, and we just had everybody basically doing, we were videotaping the labs and then having everybody watch those videotapes and then using our data to then do their own data. So Katie, I think you were in Mr. Pollock's 175 class, so you're kind of familiar with this. So for those of you who aren't that familiar, basically it's just us going through the lab, videotaping it, so that way you could see what we're doing, and then we're giving you the data, and then you just basically process the data. So that's what these labs are. So unfortunately we had to do that because I just couldn't find any good simulations. So this should be the only lab that we're going to do that with. So some things to point out. So let me bring up the lab itself. So basically the videos skip part 2. But the first part is basically just making observations of what happens when you bring a current carrying wire near a compass. So it's kind of running through and it's showing you the observations. So this part of the lab, you're basically just writing down the observations based off the video. So this is the report section. So basically you're just writing down those observations. Even though it's not, again, a full-blown report, you're just writing down the observations based off of the videos. Again, part 2, we're skipping. That's mostly just trying to tell you how to actually calculate the direction of, or the magnitude of the magnetic field from the wire based off of the angle of deflection. They also talk about it in the video, but basically you just need the equation 1 here. So this is basically telling you how to calculate that magnetic field from the magnetic field of the Earth, where up here it tells you that the magnetic field of the Earth is 5 × 10⁻⁵ Tesla. So the units for magnetic field are what's called Tesla. So part 3 always is kind of a tricky portion for students, but basically what you're doing is, at least what they do in the lab, is they're taking a wire, connecting it to a battery, so you have current running through the wire, and then they're measuring a few different distances. So here they're measuring first where you have a 40-degree deflection, and they're measuring that distance of the wire above the compass, and then measuring a few other distances. And then what you're trying to establish here is what is n. So n here is basically saying that, okay, so we're going to write the magnetic field as some constant k, we don't care what the constant is, times the distance raised to some nth power. So just means you might have, you know, k times r to the 2nd power. So it could be kr squared. And what you're trying to do in part 3 is determine exactly what this value of n is. So what you're going to do then is you're going to use the deflection angles that they tell you in the video, as well as the distances. So you're going to calculate the magnetic field using equation 1 from the angle deflections. And then the distances, they're going to tell you in centimeters. You just have to put it into meters. And then you're going to plot all that data and then take the natural log to determine what n is. Okay. Now, ultimately, you don't care what k is. So what this says is that the natural log of b is then equal to the natural log of k, but the natural log of k is just the y-intercept, so we don't actually care what k is, plus then n times the natural log of r. So basically for part 3, what you're going to do is, in Excel, you're going to plot on the vertical axis natural log of b. On the horizontal axis, you're going to plot the natural log of r. And then you should get a line that does something like this, okay? So you're gonna get some data, say here, here, maybe here. You're gonna plot a best fit line. And then where this thing runs into the x-axis here, or sorry, the y-axis, this is the natural log of k. Now again, I don't care what this is. This is not what we're caring about. So here, we're plotting the natural log of b is then equal to the natural log of k plus n times the natural log of r. So again, this is the y-intercept. We don't care. So what this thing is saying is that whatever the slope of the line is here is equal to n. Okay, that's all this thing is saying. So n then is going to be the equal to the slope of the tangent line, or not the tangent line, the best fit line that you're getting from here. Okay, so when you plot all this, you're going to get then some equation which says that y is equal to some mx plus b, right? This is what Excel is going to tell you. All you care about is what is the slope. So the slope in this case is equal to that n value. So the n value is the power dependence of r. So that's all you're doing in part 3. Okay. So all this is part 3. So you just want to make this plot. Now, parts 4 and 5 are kind of the same. I didn't part them as parts. Okay, but all part 3. So the first part is for, sorry, that was for the wire. Yeah, for a long wire. So let's write it this way. So this is part 3 for the wire. This is for the wire. Keep going. And then the next part is for a coil. So in the video, again, they're going to make a coil. They're going to measure the deflection at a few different angles. So they're going to measure the at position A, position B, and position C. And as far as you're concerned, you only care about what they have at A and B. Okay. From A and B, you're then going to use this equation, which basically says then again that you're going to take the natural log of the magnetic field at B divided by the magnetic field at A, divide all that by the natural log of 2, and then that's going to give you, again, your n value. Okay. So for the coil, what you care about is the deflection angle at A, the deflection angle at B, and then you're going to get n then is equal to the natural log of the magnetic field at B divided by the magnetic field at A, all divided by the natural log of 2. Now, n here should be a negative value, just like here. N should be a negative value. Okay. So for the coil, this is all you're doing. So you're going to plug it into this expression here, where again, oops, sorry about that. So in this case, the magnetic field at B will be equal to the magnetic field of the Earth times tangent of theta B. And then the magnetic field at A will be equal to the magnetic field of the Earth times tangent of theta A. Okay. So whatever these angles are that they give you, those are the angles that show up in here. Okay. So that's for the coil. Bar magnets, basically the same thing. They're going to measure the directions. So basically here you want to draw the direction of the magnetic field. So this portion is just to try to show you what I drew in the beginning, which was that if I have a bar magnet, let me draw it over here. This is the North Pole, this is the South Pole. Magnetic field should actually do this. So at location A here, it should point this way. This location, it should point this way. This location, it should point inward. This location, it should point this way, okay? So basically, that's just what they're gonna show you. You're gonna draw that. And the distance dependence, again, they're gonna do the same thing. They're gonna measure it at a couple different locations. Again, from that angle dependence. For the bar magnet, you're gonna use exactly the same thing. So for the bar magnet, again, you're going to say that n is simply equal to the natural log of B at 70 degrees. I'm sorry, 2 times 70 degrees. And then B at 70 degrees divided by the natural log of 2. So this will be n. And again, this should be some sort of negative value. Okay. So for each one of these sections, all you're doing is you're calculating what n is. So for part 3, you're calculating n here, and here, and here, and then just quoting what those different n values are. Okay. So again, all of this they're doing in the video, you're just watching what they're doing, recording the information that they're telling you, and then going from there. So each video is only like 2 minutes long, so they're not very long at all. So that's it. So again, just part 1 is just writing down your observations based off of the observations they show. So part 2, again, skipping. Part 3 is all the angle dependencies. Again, in the first part, you're making a XL best fit line. extracting the slope. For the next two parts, you're simply using this expression for the angles that they tell you for the deflection angles at those points. And then for this one, you're just drawing the beautiful shape. And that's pretty much it. So, like I said, so this lab is mostly just trying to get you to make observations of magnetic fields before we really start talking about magnetic fields. So again, you can see that they actually move in circles as opposed to straight lines, and that they're actually generated by currents as opposed to stationary charges. So that's the overall point of this lab. So again, unfortunately, I couldn't find simulations that kind of did all this stuff, so we just have to watch these videos, but we'll have to make do with what it is that we have. So it should be fine. Okay. So Monday, then, I'll have to type that one up, but we'll be doing Faraday's Law. So that one, we should be back to doing simulations for that one. But I'll have to look a little bit deeper on that one, but it should be fine. So any questions on these? Everybody's okay?
You said we're drawing the one, and then the bar magnet, we do have to calculate in, right?
Correct. Yeah.
Okay.
Yeah. So if you look at the way the lab is kind of set up, so the first part here, so field for a bar magnet. So the first part is just all the drawing. So it's just asking you to draw the locations and then draw what this thing should look like. And then here's the distance dependence. So so you are doing both. So you're drawing and you're also doing the distance dependence, where they're going to tell you the distance for 70 degrees. And then they're going to increase that distance by 2, and then you're going to find the deflection angle there. So at 70 degrees, you already know the deflection angle is 70. So you just need that distance dependence, and then they double that distance. So now you know the double the distance. So now they're just measuring the new deflection angle, and then you're going to use that same expression to then determine that distance dependence. So So for the bar magnet, you're doing those two things. Exactly. Good. So I think that's about it. So not too bad. And again, next week we should be back to doing simulations, so you actually get to play with stuff. So that would be great. Okay. So any other questions on this? So it shouldn't be too bad. Like I said, each video is only like 2 minutes long. It's mostly Dr. Purcell talking, except in the first video, it's Dr. Purcell and Dr. Scheller, who looks very grumpy to be there, but that's fine. Cracked me up when I was watching it, so it was fine. So, everybody's okay? Not too bad. Good. So I'll be here. So if you have any questions, definitely come back on and ask. But otherwise, it shouldn't be too bad. So it should be nice and easy.